All right. Testing, testing. We got audio? Cool. Sweet. Hey, everybody. Whoa, is this, can everyone hear me okay? Too loud, too quiet, everything good here? All right. So, hi, I'm Dan Kaminsky, and this is totally not a talk on DNS. It is also not a talk on DNSSEC. It's not even a talk on X509. This actually is not even really a talk on offensive technologies. Although, as any defensive talk goes, you're going to find something offensive that breaks other things. We are here to do defense. Defense is even in 2010, remarkably immature realm. It's very hard. It's still hard. And I don't think we've necessarily reasonably examined why these problems are still going on. What I want to do is talk about what technical steps can be taken to actually start delivering real-world defense to our customers. So, warning. This is a really ornery talk, guys. I'll just tell you straight up front, I don't think we've particularly been very good engineers in the security space. I don't think we've been very respectful of other engineering requirements. Quite specifically, when it comes to the web, who here has ever built a website, been involved with the back end of a website? Not just for breaking it, for like building stuff? Okay, so my overriding belief is that we in the security community tell you to do really pain-in-the-butt things, and we think it's okay. One of the things we say is that you should put randomized tokens in all of the URLs that you use. Yeah, it's a big pain in the butt, and I'm going to talk about why. And finally, what I want to talk about here is to explain, apparently base64 is a lot more useful than you may have thought. So that's kind of what we're going to do here. So let me set the stage. See? DNS, nowhere on this slide. Listen, HTML, JavaScript, and CSS are by a wide margin the most popular programming languages on the planet for front-end GUI design. You laugh, you know it's true. Your 8-year-old cousin can write some HTML. Your 8-year-old cousin will throw himself off the roof before he touches Win32. Whatever makes it work, man. Look, this stuff is bigger than Win32. It's bigger than Objective-C. It's bigger than Java. Let's be honest, it's even bigger than Flash in terms of how much stuff has been written in it. Why install software? Why deal with all that? You just go to kayak.com. That's why this stuff is very big. But the web has a security problem, by which I mean the web kind of is a security problem. Cross-site scripting and cross-site request forgery attacks are absolutely endemic. And SQL injection attacks are not actually going away. And injection is not limited to SQL. We have injection problems in XML, in JSON. Heck, even LDAP is in trouble. We are having some canonical bugs that we've known about for over a decade, and they're on the vast majority of what has been written. Everyone who raised your hand earlier, you have probably screwed this stuff up. Like, look to the left of you, look to the right of you, look all around you. There might be a guy in the room who hasn't screwed this up, but that's about it. Why? Why is this stuff still going wrong? Like, after all, aren't these solved problems? Don't you just use randomized tokens and validate your input, whatever that's supposed to mean? Like, why is this stuff still haunting us? Now, our traditional response in our industry is for us to say developers are stupid and lazy because it defines us as intelligent and industrious. I like this. This is great for my ego. But you know what? I got to tell you something here. If it takes them 2 years to build it and us 2 weeks to break it, who do you think has the harder job? I got a hint. It's not us. The reality is that it remains too difficult to make web browsers do surprisingly simple things. I was talking to someone very, very good web developer, someone who actually has been going to DEF CON for years. And she looks at me and she says, you know, Dan, I've been doing this forever, and I've been coming to DEF CON forever. But you know, it's $50,000 US for me to build a website. And it's $150,000 for me to get someone to come out and make the website secure. Do you know of a client that will let me charge 4 times as much for the same functionality? And I gotta be honest, I don't. I really don't. Our advice sucks. It's expensive. It's ungodly expensive. It's ungodly expensive in terms of dev hours, and it's even worse in terms of actual validation. And we think that's okay because it's security. And of course, if it's security, it has to matter. You know what? We lost and didn't even notice. Let's talk about something that is actually a wildly common piece of advice. Now, to give you a little bit of background, there's this thing called cross-site request forgery, where some other site causes a query to come into your site, and you know, their query mixes with your credentials, and bad stuff happens. And one thing that was suggested is, what if we had a randomized domain? So instead of www.foo.com, you had peruserap319.foo.com. Well, what would you have to do in order to do this? Well, let's see here. Quiet you. All application local URLs have to be rewritten. While standard HTML forms and hyperlinks are easy, we've got to edit all prior existing JavaScript. We've got to deal with all implementations of document location, opening new windows, all on-click events, all on-submit events. HTML code, by the way, might include external reference JavaScript libraries, which have to be processed as well. Because of these problems, a web application that is protected by such a solution has to be examined and tested thoroughly. Guys, this is a lot of work. Like, this is an incredible amount of work. This is as much work as actually building the damn application in the first place. This isn't something obscure. This is an everyday recommendation we make in the security industry that web people should do. This is not good. It's not like we're weak in obscure places. This is session management. Session management is not obscure. Session management is an inherent aspect of any system that allows authentication. Now, if you go back to the original history of the web wasn't particularly originally designed as an authenticated resource. All material was designed to be able to link to all other material. And let's be honest, we weren't supposed to have everything be a dynamic PHP web page. They were files in a directory. But you know what? It's 2010. It's not 1993. Over 17 years, you can actually re-engineer things to be more convenient or more mature if you actually pay attention, which is frankly something we haven't been. The canonical way that session management is done, such that when you actually access a web page, you get different content than, say, some random other person, the canonical implementation is something called cookies. These are small blobs of data that once they're given to you are reattached to every following HTTP request. So you get your cookie, and then the next time you go to the site, it's, I have my arbitrary blob. And the blob is some encoded thing that says that you logged in, provided a password, answered a phone call, whatever. The deal with cookies, though, the thing that was done 17 years ago, cookies don't care where a request came from. If you go to any random site on the internet and it has a request to Facebook, that request is going to go to Facebook not just with the attacker-controlled URL, but with your cookie. This is the heart of cross-site scripting. This is the heart of cross-site request forgery. Cookies attach to any requests that are within the scope of that cookie, whether or not they actually originated from the same site. This is a problem. I mean, obviously, other people get to play around with your password. So what we tell people in our community to do, and when we tell people to do is, no, don't use the cookie, which is automatic and just works. Instead, go ahead and take this token here and append it onto the end of every single request and never screw it up. And do all of this work so that always works right. That's what we tell people to do. Cross-site request forgery tokens are about sacrificing the automatic nature of cookies for manual integration of a token in each generated URI, no matter how expensive that must be. Can't we have something better? It's 2010. Why is this still such a hack? Like, all of this is really painful. All of it leaks. The answer why is because never mind. The answer why is because we haven't asked for anything better. Every time I've ever talked to someone about what we do about this session management problem, the response tends to be, see, this is why cookies should not work from third-party domains. If I am on badguy.com, how come a request can happen that goes to Facebook? We should just turn that off. And then I observe that that will break the web, and people are like, well, you know, sometimes you got to break a few eggs to make an omelet. Yes, screw you. No, I'm serious. Like, that is the actual, literal word-for-word response. Actually, no, it's more fuck you than screw you. But, okay. Our message really is, it doesn't matter if it's expensive. It doesn't matter if it's fragile. It doesn't matter if it breaks things. It doesn't even matter if it doesn't do a great job securing things, because there are bugs in CSRF tokens too. It's security. Obviously, you have to do it. Because we're so hard about this, instead of improving our technologies to the point where they're deployable, we do the bare minimum effort, and then we spin our wheels demanding the deployment of immature defenses. I'm done with it. I want to see better. Now, you may disagree with me. You may think all our existing solutions are good enough, and the only problem is lazy and stupid developers. You might even use the phrase insufficiently incentivized. If you think this, okay. Nothing I say is going to convince you otherwise. Maybe you'll find a cool thing later on in the slides, but you're not going to believe me. But if you agree with me, and if you think maybe our industry could recommend more effective technologies, your immediate request should be, so what are you recommending? It's not enough to curse the darkness. One must praise the light. Totally legitimate. It's the first law of securing the web. You're not allowed to break the web. You laugh. It's a point of massive contention. I am the minority opinion in the security space, and everyone in the developer space is like, yeah, we just ignore all you other guys. Check this out. Let me tell you an actual true story. How many of you people have heard about Project Mogul or the TLS renegotiation vulnerability that happened a little while ago? All right. How many of you guys know how that story ended? Yeah, I get. All right, so there was a huge IETF effort around a actually utterly beautiful bug in SSL and TLS. Been around from the beginning. It was a specification flaw. Thousands of hours of work were done. All the major crypto libraries have fixes that have come out in them. This is awesome. The fix is off by default. Why? Now, first off, as soon as I heard about the fix, I knew this is how the story was going to end. Like, I looked Marshall in the eye and like, wow, you guys did a lot of work and that ain't going to do anything. He's like, no, it'll work eventually. I'm like, no, it won't. And so, patch comes out, and when you actually look and read all the crypto patches, they say, well, the default setting is false due to problems with some common sites. Oops. It didn't matter. It's probably like 1% or 2% of sites out there. You just can't make a secure connection anymore. It's just broken. Surely that's not enough to suppress the fix getting out. No, it totally was. Completely was. You can't just say, we're going to go ahead and change something, and it's going to break a bunch of stuff in the field. And if people want to be secure, well, obviously they'll fix those things that it's just not working in the field. No. The internet does not have flag days. There's no, okay, everyone, on July 8th, 2013, we will all simultaneously stop using Internet Explorer 6. Every web developer in the world would love this. Not going to happen. Never. Never. That thing is going to live longer than I am. 2034. Look, they needed to find a way to securely downgrade for servers that did not support their fix. When they were doing the TLS code, they needed to have a retry. They didn't. They just said, well, eventually enough servers will be patched, and then this can be turned on by default. This will never be turned on by default. It will always be possible that there's a server out there that's not patched. It's a hard fact, but it's true. I don't care how many thousands of hours the security people spent, the ops guys aren't tolerating an outage, period. So the second law of securing the web. You must meet all engineering requirements. According to classical security theory, the attacker need only find one bug, while the defender must find them all. Now, this is true, but this is incomplete. I submit that the attacker need only consider one engineering requirement, while the defender must balance them all. When you are making fixes, if your fix is not fast enough, it is not good enough. If your fix is not compatible enough, if your fix is not reliable enough or usable enough, it is not good enough. And if your fix is too hard to build or deploy, as a matter of predictive fact, it will not be built, it will not be deployed. We have tremendous egos sometimes in security, but from an operational reality standpoint, you screw this stuff up, it's like your patch was never written. Literally, that's how customers respond to it. It's like, hey, I wrote a patch, this patch goes in and solves the hole. Great, I lost half my speed, I'm not deploying your stuff. In fact, it's like you wrote no patch. Where's my patch? You're like, but I got one. No. That's not a patch, that's really slow. That doesn't count as one. This is reality. This is why patching is hard. This is why testing matters, because you can screw these things up and not even realize. The way to look at it is that security is a new first-class engineering requirement. This is not the only new first-class engineering requirement we've seen this decade. Power efficiency is an extremely new requirement for consumer electronics. Management comes down and says, hey, this television you built takes too much power. And the response is, I'm pretty sure it's not going to erupt into flames, so it's obviously not taking too much power. It's like, no. It now matters how much power your television takes when the television is not being watched. Your standby power exceeds some requirement, you've got to make it use less. And they're like, okay. Now, that doesn't mean that you get to go ahead and, as your television engineer, make the screen less colorful. It's still got to be colorful, it's still got to be high res, still got to have good sound, it's still got to, manage to get good reception. It has to do all the things it did before, but now it's got to use a low power when it's asleep. It's a new requirement. It doesn't actually get to alter any of the existing stuff. And what that means is something very interesting. Means that surprisingly basic work remains to be done in security defense, because a lot of our recommendations have always assumed we get to do whatever we want because we're so important. Well, it turns out you don't. We actually have to make all of our requirements met, just like the television guys have to be less power, but television guys have to be less power while still doing all the things that were done before. So, let's start out by trying to see, is it possible to do something better than a cross-site request forgery token? And to genericize the request, to genericize the ask, we want a secure session context. We want the ability to have, when I am logged into a site, only I get to use that site. Other people in other tabs don't get to use it too. It's a small ask. You'd think it'd be done by now, but it's 2010. It ain't done. How does this secure sessions context improve security? Let's look at cross-site scripting and cross-site request forgery. They have something very interesting in common: cross-site. I submit to the audience, there are two kinds of web pages. There's BBC. BBC needs the ability to have anyone in the internet link to this particular story. Deep linking is totally required, absolutely. But you know what? I don't need yahoo.com to be able to link me 3 pages into a 4-page checkout. It's a different kind of site. We need to start treating authenticated versus unauthenticated resources as two very different things to secure. There is a very natural boundary between unauthenticated and authenticated access. Unauthenticated pages tend to be very good landing points. They tend to be very generic. They tend, if you are designing them right, to not have very dynamic content. Not even because of security, but just because of performance. Because random people from all over the internet are showing up there, maybe it should be cacheable. The performance guys have been making the unauthenticated pages more secure, at least in theory, for years, just because it keeps the site running. The authenticated pages in a site have extreme complexity. The checkout from Amazon is actually quite complicated. Online banking applications are actually quite complicated. You know what? You don't actually need the ability to deep link into one of these applications. If you had a strong session context, you could have large numbers of what we normally call flaws, and none of them would be exploitable because you wouldn't be able to link into them at all. Oh, this page is going to reflect whatever comes into the 83rd hidden form field. You know what? I don't care. It came in from a remote site. It's not exploitable anymore. That's where we need to start being able to get. Now, it's not like devs haven't thought of this. I cannot tell you the number of times I have seen people try to implement what is referred to as server-side referrer checking. Who here knows what the referrer flag is in an HTTP, a referrer header is in an HTTP request? All right, so check it out. If you are on badguy.com and there's an image link, say, to goodguy.com, that HTTP request is going to come in, and generally, the unfortunate word, but generally, there will be a header that said, hey, I'm asking for the good guy image here. And by the way, this is from badguy.com, just so you know. So lots of devs have said, why don't I just look at this HTTP header, and if I see it's from some other site, I just ban them. Go ahead and block them. It's very easy to write. People can write it in 10 minutes. And you know what? They do. Lots of content management systems have this very functionality. Developers finding a defensive technology that is easy and non-disruptive to implement, they actually do the work. It's not that they're lazy and stupid, it's that they want something simple and straightforward and non-intrusive to implement. This looks like it is. We tell them not to use it. We tell them, no. Referrer headers can be spoofed using XML HTTP and by using Flash, as demonstrated by a Meet client in Rapid7, and therefore cannot be trusted. That is from the canonical guide to why you should not use server-side referrer checking. There's a problem. It's not true. A Meet client and Rapid7 got this fixed years ago. Referrer headers have been unspoofable since about 2007. It's not that it's perfect, because let me tell you, nothing's perfect in the web browser. However, as part of the security model of every single browser in the field and every single plugin in the field, if you can spoof a referrer header, it is a bug. It will be fixed in an emergency patch, or in a the monthly patch cycle or whatnot. So can't we use this then? It's secure. There's no way to spoof it, so security doesn't have a problem. No, no. Application compatibility is why you can't use this technique. It turns out that there are many, many ways of navigating from one page to another page. You can follow a link. You can change document location href in JavaScript. You can follow a 302 redirect. You can follow a meta HTTP equiv refresh link. There's window open. Is the referrer header there? Maybe. Depends on the browser, depends on the call, depends on the time of day. I don't care. You can't depend on it actually being there. It's really annoying. And that is without the security tools butting in. There's this hilarious page on the WordPress site that says, here's how you administer your WordPress site if you have any of these security tools installed. So here's what you do if you have Norton Internet Security. Here's what you do if you have Provoxy. Here's what you do if you have McAfee. The thing is a suicide note for web administration. It's a tragedy. And that's to say nothing about all the various, this isn't very well known. About 20% of HTTP traffic on the open internet comes from behind a proxy. generally a squid proxy. And a bunch of these proxies also remove referrer headers. Now, I can understand why referrer headers might be removed. Like, there's a little bit of a privacy link, and, there's some things called dynamic cross-site request forgery attacks. But could they have left the referrer header when it was the same domain? Like, really? Like, there's no privacy issue. You're using the site. You don't need to remove the header there. I know. One security technology interfering with another security technology, that could never happen. Crap. Let's talk about failing open. Who here thinks failing open's a good idea? Good. So, a lot of devs have said this. Well, all right, there might be situations where there's not an XSRF header. However, if we were to see that there's a conflict, in other words, if we're talking to one of the 60 or 70%, or maybe even 80% of people who will give us referrer headers, if we're talking to them and they tell us very clearly there's a problem, why don't we at least block those situations? In other words, if the risk information is missing, let them through. But if they have a clear sign that there's a problem, okay, maybe we should stop them. At least we'll handle 80% of the threat, right? Problem is, as I said earlier, there's a million ways to browse from one site to another. And as an attacker, you can actually very reliably send a request such that a referrer header does not show up on a foreign site. And the actual most reliable way to do that is with a meta HTTP equiv refresh request. So what you do is you have a little iframe. You say, oh, hey, go over to that site over there with a refresh and get this URL. What will happen is the request will go from badguy.com to goodguy.com. It will have the attacker-controlled URL. It'll have the user's cookie. It will have no referrer header. And on all these content management systems, it will just work. It will fail open, and it will fail as every fail open system ever does. So what about client side? So seeing all of these nasty things on the wire that are altering headers, I basically said, okay, what if we can't rely on anything on the server side to tell us what went wrong? Could we detect that there was some outside interference with our session inside of the client? Now, this is a little heretical. You're never supposed to trust the client. How could you trust the client? It is, at the end of the day, the web browser, the client, that knows the source of a navigation request. If you have two tabs open, and one of those tabs is good guy, and one of those tabs is bad guy, and bad guy's tab makes a request for good guy's content, it is only the browser that knows that happened. And it is only by dint of what it puts into an HTTP header that allows the server to guess anything. Your client, when your client has 400 megs, 500 megs of RAM allocated, and that RAM is moving all the time, over the course of 10 minutes, your browser is cycled over about 3 or 4 gigabytes of state. Things have changed dramatically over a small period of time. Very little of what has changed in the client is actually put on the wire and sent to the server, and that's okay. But if we want to know this fairly obscure thing, which is who actually made that ask, we actually maybe need, at some point, need to get that information out of the client. Now, there are two problems when you're running this stuff client-side. If you're running this stuff client-side, it means that the server is going ahead and getting requests, and it doesn't know where the request came from. It doesn't know who provided it. So it's going to send back whatever it's going to send back. And the only thing we can do is, in the client, say, wait a second, you sent me stuff, but I need to know if I can reject it. And I need to be able to reject it for a cross-site script, and I need to be able to reject it for a cross-site request forgery attack. Is that possible? So I came up with this concept, which I'm calling interpreter suicide. And the general idea is as follows. A web page is not actually loaded all at once. In order to read the 20,000th byte, you have to have parsed the 100th byte. That's just the way parsers function. What if we could find something at the 100th byte, and if it said, wait a second, something's wrong here, this is a cross-session communication, abort. Stop this page from actually getting to the point where something bad might happen. Is that possible? It turns out that it is. There are 4 strategies we can use. The first strategy is renavigation. So we're going ahead, we realize something is wrong. Okay, something's wrong. We send an event saying, hey, navigate to a login page. Go somewhere else. This is not enough. See, the way that browsers work internally, they have a parser thread, and it goes through and it reads out all those bytes, and it's throwing stuff into a document object as it continues its parsing. Well, if you tell the window, which is kind of the parent of the document, hey, you got to go somewhere else, the window is going to go ahead and go, oh man, I got to go clean some stuff up, and it's going to kind of re-navigate away on its own schedule. The document's going to keep parsing, though, which means we're going to go from byte 100, where we're safe, to byte 20,000, where there might be some malicious reflected information. So we're kind of in trouble. But it turns out we can combine these methods. The next thing we can try is replacement. I said earlier, the bytes from the network were being parsed and pushed into a document object. That's what happens. Bytes come in, they're parsed as HTML, the HTML gets parsed, and stuff happens to what's called the DOM, the document object model. What if we just went ahead and said, hey, I actually know exactly what's supposed to be in the DOM right now? Nothing. Holy crap, there's trouble. Destroy everything. So you actually set the inner HTML of document body to null. Well, now what happens is very interesting. All these bytes are streaming in over the network, but the document object is no longer hooked up to those incoming bytes. It's just hooked up to the blank text. So effectively, those bytes are neutered. They can no longer actually execute anything. This works well. The third thing that we could try is to repeat. So we basically say, look, I got a script block here. It's, before I can parse anything else in this document, I got to wait for this code to stop running. And so what we do is we put it into a loop. We just say, I'm never done. While forever, just keep setting this value. Or call some external function that takes a few milliseconds. You don't let the thing move on. You just keep it in a tight loop. The fourth thing you could try doesn't work. Actually, one of my friends, Brandon Crichton, better known as C-Stone, broke this one. Normally, when you're using a JavaScript interpreter, if you call a non-existent function, it would seem that JavaScript stops running. It's just like, oh, I hit an error and I'm done and I'm not doing anything more. You would think that'd be enough, but no. Because if some VB script shows up, that's a different interpreter and that thing can still run. And worse, the attacker can inject what's called an iframe. This is an internal frame. It's a little window into some other page, and that thing will actually reinstantiate its own JavaScript interpreter. So no, you can't just drive your JavaScript interpreter into a brick wall to stop execution. The thing will actually come back to life. So what does this realistically look like? Upon detecting an issue, we set the document location href to a dest of cnn.com. We replace document body inner HTML with a quote, nothing. While that thing is nothing, we repeat, so we just keep going in a tight loop. If you do these 3 things here, you will never alert dest. It just won't happen. You will also never alert 1. That cannot happen either. Now you might say, but Dan, come on, there's lots of different browsers out there. Maybe some will parse HTML a little differently. So it turns out, by the rules of JavaScript, by the actual fundamental underlying design, this can never happen. Suppose you have 2 script blocks. First script block declares foo to be equal to 1. The second script block does alert foo. If the second alert block could ever be run before the first one completed, then the second alert block's output could never be predicted. It would effectively be impossible to write a JavaScript application and have any hope of it behaving in a predictable manner. So effectively, we are using a design artifact of JavaScript itself to allow us to atomically say, this none shall pass past this point. It's kind of a neat trick. If you can get around it, let me know. I've spent some time trying. Now, what about cross-site request forgery? We have a little bit of a problem. And this little bit of a problem is that for cross-site scripting, what happens is the attacker causes a request. This is for reflected cross-site scripting anyway. The attacker causes a request. The request causes a response with some attacker-controlled content, and some of that content is interpreted as script. That script now goes ahead and loads attacker content, and all hell breaks loose. Can we do, in cross-site request forgery, there's a fundamental difference in that nothing cares about what comes back. The malicious action happened only because the request was sent. When the attacker content was mixed with the user's cookie, stuff blew up. So it doesn't matter, if we have this great test here, the test is too late. What do? Well, what if we actually had the response matter in a cross-site request? So in other words, what if the response to an untokened request was a blob of JavaScript? Said, you want me to go ahead and do this action? Hey, run this JavaScript just so I can see for sure that everything's okay. And the JavaScript has the magic test, and if the test has failed, then the interpreter suicide happens, and everything is hunky-dory. This works well. It has something of a performance impact, but it functions. The bigger issue is application compatibility. Suppose you aren't just sending the browser to an endpoint. Suppose you're sending, these funky AJAX calls or even Flash to a active what's called REST endpoint. These are the things that tend to be vulnerable to cross-site request forgery attacks. It's very tricky to differentiate that which is the actual browser, which understands JavaScript, to that which is something that is loaded within the browser. XML HTTP request and Flash both borrow the browser's HTTP stack. They fundamentally look like the browser. Now, they operate a little differently. A web browser itself is very good at doing cross-site domain access. So if you're at badguy.com, it's very easy for you to make a request over to goodguy.com. If you're using Flash, you're using XML HTTP request, it's actually very tricky. It didn't used to be as tricky, but it's become much, much harder. These things, these extra plugins, they're not like the browser. They don't automatically execute JavaScript unless they're specially programmed to. Now, you could add code so that they interrogate what actually happens to see, I got this response. Let me see. Okay, let me pull some stuff out. This is actually a lot of work. And if I wanted to do a lot of work, I'd be putting an extra token onto the get header. So I've not saved myself any effort. It's just as much work also to add a randomized header. Every single time that I go ahead and I pull up this object, I need to add stuff. It's a big mess. What seems to work is as follows. If when you actually make the request, if when you actually instantiate the object, the XML HTTP request object or the Flash object for doing that sort of AJAX-y stuff, if you actually overload that object such that when the send call is called, it first tacks on an extra header, now you're in a better place. Because now, instead of having to go ahead and write code to each individual instantiation, there's just one global instantiation that you change that says, oh, hey, whenever you go ahead and make a request, tack this little piece on. That works a lot better. What test could we use in order to find out that there's been some cross-site activity? So we've found out now that, yes, it is possible to, if we know there's been something that's injecting into our session, we can deal with it. How do we know? What do we use? Do we have anything? Now things get hard. So I wanted to go ahead and use the window history object. This should have been able to tell me, hey, the last thing that accessed this page is, badguy.com. But it turns out that window history has been locked down and it's just a big list of integers. Document referrer looked good. This is kind of like the referrer header, but it is, sorry, these lights are really hot. All right. Anyway. So the thinking was document referrer never shows up on the wire. It's also spelled correctly, thank you very much. So because it's not on the wire, nothing should be interfering with it. However, support across navigational types is also really messy for document referrer. This is actually a really good way to fingerprint which browser you're using. God damn it! It was so beautiful. Now you could say, oh, well, we'll just tell our developers how to write their website. We'll just mandate that they can only use ahref for linking between pages. Yeah, it turns out you don't get to tell a dev how to write his page. He just kind of laughs at you. And anyway, there's really just a lot of different methods, and you need to find them all, and you need to update them all. And if you ever miss one, the page just silently breaks in weird ways. There's some possibility of overwriting prototypes, but it'll never be reliable. So essentially, we have a lot of unspecified by any standard behavior here, and it's preventing us from being able to use defenses. What we really want is some way to say, okay, can I mark this window? This tab is a logged-in tab. Any other tab is not allowed to be a logged-in tab, but this one is good. So I thought, what about window.name? The window.name entity is really very interesting. It is basically a cookie, not for a domain, but for a particular tab that you might have open. What if we made window.name be a magic cookie in and of itself? So when you log in, it gets set to some certain value, and then every page you go to says, wait, does this window have the right name to allow browsing? This seemed like a great trick. So there's a problem. Problem is that window name is preserved as a window browses across domain boundaries. There's a guy, kid really, goes by the name of Kuza55. He is the greatest cross-site scripter in the universe. And no, he really is. He's terrifying. I was talking to him, and I'm like, dude, I'm trying to figure out how to get this weird character through this filter. What would you recommend? And he looks at me. He's like, Dan, just put your exploit in the name variable and navigate yourself to the site that you need to navigate to and eval name. And get on with your life. I'm like, oh. So it turns out that when you have a window and whatever magic value you give to it, you can go to some completely different page, completely different domain, it's still going to be there. So in Kuza's case, he was just saying, well, I'll just eval it. And he said he doesn't come up with this method. Some guy, Giorgio Mayone, came up with it. So the attack against my system of using window.name was as follows. You go ahead and you can have, say, 5 tabs open. One of those tabs can actually open another one. It can actually have what's called a handle to the other tab. That means that even though it can't see what's inside, it can't go ahead and, oh, no, that's a different domain. I'm going to go read out your bank account information. It can't look at what's in there, but that doesn't mean it's powerless. It can still navigate that other tab. It can still send it to other locations. So what it will do is it'll sit there. It'll wait until you actually go to the bank, and it can go ahead and find out because of all the various history leaking things. It can navigate you from the bank, where the window name token shows up, to its own domain. Now, it is allowed to read inside of that page, because after all, it's the same domain. It reads the window.name variable, because the window.name variable survives browsing. And then it runs the window.back method that sends it back to where it came from. So now the bad guy has your magic security token, and you're mostly none the wiser. There are probably more elegant attacks than this, but this is enough for me to say, no, it's not good enough. It's not going to work. Meta note. When you're doing defense, yes, you need to worry about performance and compatibility and reliability and all that stuff, but don't make another crappy security defense that doesn't actually work. I was very excited about window name. Why am I here telling you about it? Because I was very excited and it didn't work, and damn it, we need to talk more about the things that don't work. The world has enough defensive technology that's totally useless. Thank you very much. So then I started looking at HTML5. And HTML5 has something called session storage. This is a store that is tagged not just to a domain, but to a window. And I'm thinking, great, this is exactly what I need. This is surely where I can put in some magic tokens that no one else can manipulate. It says, okay, this is now the logged in magic window. The problem is it's the same stuff. The foreign domain can go ahead. It can navigate us around. It can navigate our window. They can't extract the token because window session storage, unlike window name, is actually also tied to the domain. But they can still move us around. And when they move us around, it's their chosen URL with our cookie and our session storage. So we're still kind of hosed. So, okay, it's 2010, and despite an extraordinarily long research effort, it is clear there is no straightforward way to establish a session that is locked against outside interlopers. Unless, of course, you want to just run a second web browser. Oh, will you look at that? What's the advice I'm seeing everywhere? You should run multiple web browsers and use only one web browser for your bank. Yes, that does work. Maybe we can give people a better to-use system. A variant of session storage is possibly fixable. I've actually been starting to work with the HTML5 guys. What I think we ultimately need is a window new session variable. And this thing is set when a navigation occurs from a foreign domain. So what we need is a way to know, hey, badguy.com did something to get us here. Force the user to relog in, do whatever, I don't care. But something came in from outside of this session and is using our credentials. Do something about it. It wouldn't be trivial. You need to have some stuff in there to deal with the single sign-on systems from Facebook Connect and Google Auth. I don't care. But the point is something as basic as simple authentication on a web page is still broken. And that's just embarrassing. We need better. I'm trying to get that out. So that's kind of fun. That was actually the most work that I've been doing in this space. And then I had kind of a side project. And this talk's going over a bit. We'll talk in about 20 minutes. There's something else I've been playing with that I think you guys will like. Input validation. Let's talk about this. A man has a problem with a parser. He puts a regular expression filter in front of it. He now has two problems. I am not a fan of regular expressions. I encourage everyone to look up what I call Bob Ince's law. I mean, it's actually kind of true. It seems it is very good that in 2010, people have finally realized that parsing something with the complexity of this is, by the way, these are graphs of web pages. There are relationships between tags. This tag encloses this tag, encloses this batch of stuff. I mean, HTML is actually really complicated. That's the ultimate complexity view of Wired and CNN. Parsing something with the complexity of this with that. This is not actually a good idea. Exact quote, I was strutting like a peacock when I wrote that, followed quickly by eating crow when I ran that. I never did get it working right. I'm still not sure what I was trying to do. Guys, was there ever a reason we thought regular expressions were actually a good idea? Like, seriously? Like what the hell's that? That parses 4 numbers. It's 3 lines. Oh, God, the thing wouldn't fit on the slide. Okay, I'm being ornery, but I'm being that ornery. Many uses of regular expressions for input validation, they're not for implementing complex rules for input. If you've ever seen the hackers.org cheat sheet for cross-site scripting, you know why all of those things work? They work because regular expressions don't. It is a necessary procedure for many systems to be able to integrate potentially attacker-supplied strings into commands and queries otherwise written by a programmer. The challenge, the game, if you will, is to keep the user's substrings separate from the actual programmer stuff. And so what we see regex is used ultimately for are replacing characters, for escaping. Now, I'm going to tell you, I don't think escaping works very well. I just don't. The profusion of SQL and XML and JSON and LDAP injection shows us it is ultimately very difficult to know if you have two parsers. I have this one and I have this one, and I need to keep them in sync. That's actually really difficult. Things were easier when we had ASCII, okay? When there were 60 characters, 70 characters, 80 characters, you could maybe deal with that. Once Unicode came into the picture, and especially this horrifyingly wonderful thing called best fit matching, guys, you just don't know. Escaping is a war on a character-by-character basis. Are you bad yet? How about you? Maybe this one. Are you the correct kind of best fit slash that 3 tiers down is going to be turned into a real slash that's going to alter the parser? It's a disaster. It's a mess. And just as cross-site request forgery defenses struggle with needing to be dotted all around a code base, so too do injection defenses. And I was interested, what else could we try? Well, there are some various other things that are brought up. Parameterization. This is the gold standard. The idea here is the programmer code goes down this channel, and the attacker code go down this channel. And because they're two totally different channels, and they're all very distant from each other, there's no possibility the two will ever be confused. This works. This also sucks. And that matters. That absolutely matters. Parameterization, stored procedures, the priesthood of the database administrator having to beg to write lines of code. This stuff is a problem. This is not an effective or efficient solution. We've been thinking for a long time, well, it's secure, so it's good enough. You know what? If it makes your developers 10% as efficient, it's not good enough. It also, however, what kind of parameterized solution you've seen, they always tend to get, your parameterization stuff always tends to get smushed together in the end when the average web application, or serious web application, you might have 2 tiers, 3 tiers, 4 tiers. I promise you, what was kept religiously separate between the first and the second tier, man, it's just one blob of crap by the fourth. That's just reality. Then there are Pascal strings. Pascal strings involve length fields being prepended before each batch of text. And because you end up always having multiple series of text that are smushed together, you end up with overlapping length fields. Who here giggles whenever you see overlapping length fields? Yeah. The exact quote would be, external lengths lead to malloc, internal lengths lead to memcopy leads to suffering. I will never recommend length fields. They always lead to pain. There's some technology called taint tracking, where bytes are marked with, this byte, this was a bad byte, this was an attacker-controlled byte. Don't do anything bad with this byte, it's a tainted byte. In the real world, as soon as you try to do something useful, you just say, oh, no, everything's cool. I don't know what's going on, but everything's cool. I mean, this is just what happens. I've never seen a good taint system. One could be written, but I'm telling you, I ain't seen it. What about randomized terminators? MIME actually is where I learned about this approach. The idea is rather than running a war on a character-by-character basis, what if we just have some huge random blob that we're going to be looking for? And that's how we know whatever this section is, we're done. And MIME does this. MIME says, next part, here's some big random code. Whatever the hell shows up in here, it's all bad stuff until that particular random thing is terminated. This is actually not ineffective. This can be huge. This is like the ASLR of text handling. It's actually portable to other protocols, and I've started to refer to it as tree locking. Now let me show you the very simplest mode of tree locking in XML. Let's suppose I have something where there's a foo tag, and inside of that there's an evil tag, and then XXX. All right, so the XXX is attacker controlled. The attacker obviously normally would say, well, I'm going to go ahead and close evil, and then I'm going to have some other stuff, and then I'll close that, and I'll have my little injection working. It'll be great. But what if the attacker is kind of stuck? What if they're trapped between two randomized tags? They can put whatever they want there, but they don't know what they want. That actually works kind of well. Implementation-wise, is very straightforward. I'm running low on time, so I'm not going to go through it, but it's in the slides. This is a slow way. It could be done much faster. There is a risk, and this risk is an iceberg that we probably just have not noticed in existing stuff. Let's suppose you have a batch of XML, and the batch of XML says, well, I've got a book, and then there's a title, and then Lang Ing, and it's Harry Potter, and a price of $29.99, then we close the book. This is our little XML data set. There is a search language for XML called XPath. It's very popular. Why? Because it is super easy to use. An XPath search for /book/title will return all titles within books. How easy and straightforward is that? How could you possibly get any easier? Aha! You could also search for /title. And that just gives you all titles, no matter where in the XML tree that happens to show up. And now we have our potential risk. Because in real-world enterprise systems, XML blobs get grown more and more and more. And you might have a section up at the top that came in from the attacker. And that has some XML, but that's all attacker XML. And I, with tree locking, was trying to keep someone in that little thing up in the corner. And I can do that. But what if the code 4 tiers down says, show me every tag, no matter where it happens to be, that's run arbitrary code? It's not just going to find it in the programmer-controlled stuff from the 3rd tier. It's going to find it in the attacker-controlled stuff from the 1st. Because the programmer wrote the simple query. The simple query is, give me all the sensitive content. I don't know or care where that might have shown up. And this is a problem. This is actually potentially a problem for all SAX parsers out there. SAX parsers are streaming parsers. This is a problem for a lot of naive implementations. Something big is going to be vulnerable to this. Now, what about JSON? JSON, unlike XML, does not have terminating strings. So before we were able to have this magic XML blob, which then needed to be closed. With JSON, all we have are, have you ever heard of the nickname for these curly braces? Open stash and close stash? I think it's great. Well, I thought, well, I could go ahead and use JSON comments. I could say tree lock, 1, 2, 3, 4, 8, and then you have to close with a close tree lock 1, 2, 3, 4, 8. Seemed like a great idea, except JSON parsers don't actually support comments. Why? Because somebody might use something significant with them. More importantly, it's not actually the right thing to do to use things like this, because the problem is that this support fails open. Suppose you have a JSON parser that handles comments but does not actually implement tree locking. Oh well, it still parses. It still looks like it works. It fails open. And systems that fail open tend to, well, fail. So then I started thinking, instead of using these randomized terminators, what if I went ahead and encrypted big blocks of text inside of JSON? So I'd say, I have my foo, and then I have a tree lock section, and it has a key, and then there's lock data inside that it would then get decrypted by the key right above. And this will be great. And then I realized the crypto was totally worthless. With the base64 encoding, the attacker had no bytes that could escape this particular chunk of the tree. They were basically, instead of being escaped, a blacklist, there was a whitelist. You have 64 characters. This is what you get to use. Okay. So now let's say I flipped it. Let's say I had crypto but no base64. Well, the attacker couldn't reliably run an attack, but eventually he would randomly hit on some bytes that would go ahead and cause problems. So the value never came from the crypto. The value came from the encoding, came from whitelisting to the base64 character set. So once again, no point to encrypting data when the key is right next to the encrypted data. Again, let me repeat. There's no point to encrypting data when the key is right next to the encrypted data. I say this twice because the number of database administrators who think this is a wonderful internet-changing idea is apocalyptically large. You might say base64 is slow. No, it's pretty fast. Actually, I don't know why, but it was faster to cat dev null when it was base64 encoded first. What? There is some data expansion, but compression handles it pretty well. And what you end up with is, all right, you have a test, you have a tree-locked blob, and it's some big base64 blob. You decode it, and it's like, oh, okay, here you go. This test is evil tono. This approach is not just for JSON. It works well for LDAP. And note, we can have overlapping base64, so we can chunk out the OU field and the O field. And of course, it works for raw XML as well. It works for SQL. And it works really interestingly for SQL. Standard SQL injection, select count star from foo, where x equals, then it's this big blob of x or 1 equals 1, and then you get 3. Suppose you go ahead and you have that actually be select count star from foo, where x equals base64, decode, big blob of stuff. Now you get 0. This is an alternate encoding. I am not actually the first person to have this class of idea. In fact, some random guy in the Czech Republic posted on the MySQL list. He's like, I am so tired of SQL injection, I'm just going to turn everything into ASCII 1s and 0s. Inject that. And of course, people made fun of him. And they're like, yeah, well, you've just come up with simply another way of escaping your data. What could possibly be significant about that? You know what? Random little Czech dude was right. Okay, look. You know what ECCAB3IAJZENPSCX is never going to be parsed as? That is never going to be parsed as SQL. That is never going to be parsed as JSON. That is never going to be parsed as LDAP. When we had that base64 decode function right here, we are type safe going in to this function. The actual parser, the SQL parser is going to see this, and it is only ever going to see it as a string. There is going to be a response from that function, that base64 decode function. That response is going to be seen as a string literal. There is going to be a type associated with that response. And that type is not going to be a subquery. That type is not going to be an or, an and, a command, a function, and anything. It's gonna be a string. We're actually going to have type safety again. In this model, if you actually base64 encode your data as it goes into the database, you aren't just speaking base64 randomly, you are speaking to the parser itself. And you are saying, this data here needs to be parsed in this particular way, and never shall you parse it any other. That's actually kind of awesome. Now I know what you're saying. Are you sure we can't just do escaping? I mean, how hard could it be to parse Unicode? Goddamn Unicode. All right, so check this out. I said earlier this wasn't a talk about X509. I lied a little. There's a little bit of awesome X509 stuff I didn't talk about last year. So Last year, any of you remember this whole null terminator and a certificate an SSL certificate brouhaha? So one of the responses that I got back was, oh, okay, so apparently null is a banned character for X509 certificates. We got to make sure not to have a null. And indeed, that is true. However, there's more than one number that equals 0 in Unicode. So what you can have, so UTF-8 is a 8-bit usually encoding. And by usually, I mean sometimes it's 8-bit, sometimes it's 16-bit, sometimes it's 24-bit, sometimes it's 32-bit. Yeah, you really don't know. You can have what's called an overwide character. This is a character that normally could be described in a small number of bytes, but you know, if you want to put extra, that works too. So OXCO, OX80 is an overwide null. It's another way of saying 0. If you put that in a certificate, Windows Crypto API would also treat it as a null. Okay, we'll ban that one too. Okay, there were 4 other ways of expressing null that I knew of. This is to say nothing about what's called best fit matching, where, well, that looks enough like a slash, or enough like a dot, or enough like a dash. Guys, the problem with implementing 2 parsers is you just don't know. The great thing about my base64 solution, you always know. Hey, I don't care what Unicode's in there, but this is what SQL is going to see. SQL is going to see a string coming into a function, and the function's going to return a string, and I am done with having SQL injection. Thank you very much. So there's some related work from called Dejector. You guys should look into it. There are some issues may justify base 32. Implementation notes. This I actually do want to talk about. I am working on getting us fast base64. You can actually get a stored procedure for MySQL today, which does base64 encoding. It is not very fast, but man, it works. We're working on building user-defined functions for both MySQL and Postgres. Oracle and Microsoft will be coming soon. The long-term dream is to have this stuff in the database itself. Because at the end of the day, I want a way to natively say, hey, database, this is an attacker-controlled string. Don't interpret it as anything else. So I think I already just said performance, it remains a major issue, and we need to deal with that. Safety. There is one canonical bug of base64 implementations. Make sure yours does not have it. There are only 64 valid characters for base64. You wouldn't believe that people have screwed up what happens if one of the other 192 shows up. They totally often screw that up, so be very careful. I want to talk about debuggability before I finish this talk. If you have ever had the pleasure of parsing a protocol that uses large amounts of base64 encoded C data blobs in XML, you probably think I'm an idiot. Let me tell you, the reason why those protocols that you may have parsed were hard to deal with is because it wasn't just base64 blobs, there was crypto. And the crypto was set up so that you had to be a, crypto god to get the decryption key. So what you ended up with was large amounts of data moving over the network that were encrypted with keys that you could never get your hands on. Okay, that's a problem. My approach seems to be better because I'm saying never actually encrypt the data. You're just putting it in base64 to prevent confusion with your actual programmer supplied data. What I think might actually make this approach popular with developers is it's easy. Developers like string interpolation. They like it a lot. They love saying things like query equals select star from table where fname equals fname and country equals country. They love doing this. And in fact, if they have to go ahead and bash pieces of strings together using tons of punctuation, my God, they'll do that too. Why are they doing this instead of all the parameterization that we tell them to? there is something called Fitts' Law. Does anyone here know what Fitts' Law is, or knew before walked in the room? Fitts' Law says that the closer two things are and the bigger they are, the faster it is you can work with them. I think Fitts' Law is true for programmers. This is usually UI law. I think programmers want code and data to be right up next to each other, because when they're thinking of them, they're thinking of the data going into the code. They don't want the code over here and the data over here, because that's not how their brains work. And they will actively work to get those things as close as possible, and then we get to go ahead and spend a whole bunch of money forcing them to unwrite it and making it good. I want to make the way they write code the secure way. What if you had a second interpolation syntax? What if you could say star dollar sign table, or star exclamation point table, or dollar sign exclamation point table, dollar sign exclamation point F name? And what if the actual interpolation decode of that was itself safe base64? Now you could go ahead and develop in your native style. You could develop easily and happily, and by the way, very quickly see, as a security auditor and as a DBA, the strings that I'm getting from the outside world are all encoded in a way that they will always be seen as safe strings. The programmer is happy because he gets a useful interpolation syntax. The DBA is happy because he sees what he's getting is safely typed. The security auditor is happy because, you know what? No more injections. This is a better way to play the game. So, to summarize, and thank you all for your patience, most of this talk has been about how to protect networks. But you can't defend without good offensive knowledge. So, the offensive stuff I've talked about first showed you that if you have a system that is doing referrer checking, you can very easily bypass the referrer checking using meta HTTP refresh, or actually by bouncing between HTTP and HTTPS requests. That also works. I've pointed out that override nulls and override characters in general are a way to get around a lot of filters. I reminded you guys about eval name, because that is ultimately how all cross-site scripting attacks should be implemented. And we talked about how parsers that search the tree and don't care where in the tree they find something are ultimately going to be vulnerable to attack. In terms of defenses, defense is hard. It requires being aware of a whole ton of issues that have nothing to do with leet security. If you are not obsessed with all these other issues, people just aren't going to deploy your stuff. I mean, like, nice job, kid. Your stuff doesn't work in the field. Session handling for browsers remains a total embarrassment. It is possible to generate a strong binding between a user and their actual login session, but it requires throwing tokens on at extraordinary expense. We need better. We can possibly get it. Finally, the last thing we talked about was that base64 as an encoding mechanism for potentially attacker-controlled strings bypasses entire classes of failures that we've been having in the last 10 years of trying to deal with SQL and other injections. As a final note, it's not like developers haven't had to escape. Exclamation points or apostrophes show up all the time. Developers have had to deal with escaping anyway. They've needed a better way. With base64, we can support Irish names. That's what I got. So, I am actually open for questions if anyone has a thought, observation, or especially an attack against any of the stuff I brought up. And by the way, I can't emphasize enough, please break my stuff. Better you than anyone else. Is the other mic on? Oh, did I pick the wrong one? Testing, testing. Yeah, I did. I will trade you.
I'm not a developer, so, but I think couldn't you use for the SQL stuff, wouldn't it be sufficient to use prepared statements?
What was it? Oh, they suck. They suck. Let's like admit when we are, at least admit when you're telling a developer to do something that sucks. Hi. Okay, so this really happens. DBAs will say, you want to write a new query to the database? I have to audit it. I have to know if it's good. I have to know if it's safe. I'll tell you what lines of code you get to write. This sucks. Like, this is not a flexible way to live your life. Okay, you want to manage like resource consumption? Fine. Have a way of restricting resources for a execution context. But this model we have where you have to beg a DBA in order to be able to code something with a stored procedure, this is, it's job security, but it's not actually an efficient way to build stuff.
Not as a stored procedure, but prepared statement. Like in PHP, you have to...
It sucks.
Okay,
It sucks. Look, okay, let me clarify what I mean by it sucks. The problem is so I actually ran an exercise with some of my friends on this. We're sitting at a whiteboard. I'm like, all right, I'm going to show you 2 lines of code. And these 2 lines of code are, here's defining a string, and it's, with pluses and whatnot, it's chunked together like Legos. And now I'm going to execute that string. And I'm done. I've moved on with my life. Now I'm going to convert that into a prepared statement. Okay, so I need to go ahead and add this string, and then it has question marks. And then I say, now I want you to find the first question mark and replace it with this variable. Now I want to find the second question mark and replace it with this variable. And, oh, I added an argument. Now I need to update each of those integers to make sure that everything is aligned correctly. This sucks. String concatenation was working great. And the prepared statement stuff, this comes back to this. We don't register when we're giving painful advice. Developer pain does not exist in our reality because all we tend to care about is it secure, not is it actually easy to write.
But sorry, that's exactly the same what you're doing with your base 64 decoding, because you're treating or you're changing the default behavior, the default thinking of SQL developers or database developers. And it doesn't really matter if it's the stuff proposed or if it's base 64, it's just the same. But you can yes, you can just keep your pluses in your statement. But actually the developers have to include something special into their statements. So it's pretty much the same. They have to change their code.
You would be right if I hadn't proposed the alternate syntax. Base 64, if it's just another escaping. So here's the problem, one of the problems with escaping. And I actually skipped over this slide because of time. You see this if you spend some time auditing code. So data comes in from the outside world. And the first thing we do is we go ahead and we run this escape statement on it. So now it's supposed to be safe. 5 functions down, all the way through this big, huge mess, we finally bother to go ahead and use the various values that were escaped. Fits law. You developer down here is like, I don't know if my stuff has been escaped yet. Maybe I have to re-escape it. And now you get into this wonderful joy of multi-escape bugs. And so then people are like, well, maybe there's a problem with the escaping. And they go ahead and they look 5 levels back. And then the security auditor shows up and he's like, I need a static analyzer to figure out whether there's actually security going on or not. Now, I want to show you something about this line right here. If I'm a security auditor, I look at BD $! table, and I immediately know that thing is coming out, and that's coming out in base 64, and it's being interpreted by the database engine as a base 64 blob. If I'm a developer and I see this, I see, hey, that's 1 line of code. That's something that I can treat in the same way I have been writing code insecurely. I have a couple more characters, but it's in line. It doesn't violate Fitts law. It's still pretty easy to use. What I'm saying is if we want secure systems, we need to make secure systems look as much as possible like the insecure stuff developers want to write anyway. And I think this actually looks pretty good.
But actually, it's not that much of a difference. Like when you use prepared statements, you don't have to check for them being escaped at all. So actually, it's pretty much the same. You rely on something, on some data format, and you do the same when you have prepared statements. But maybe we can take this discussion offline. I don't know, it can go on for like another half an hour probably.
You may disagree. Look, I don't mean that, I want to be clear. I don't mean that as an insult. I don't mean that as a negative statement. Like, there's no way I could convince everyone in this room, or even many people who believed it at first, that prepared statements are actually a bad thing. All I can tell you is that the marketplace of developers has basically decided that they don't want to use it unless they're absolutely forced to. Our reaction has been to absolutely force them to. Have you ever seen a prepared statement where a developer wasn't required to write one? Because I haven't. When it's policy, they'll write it that way. Here, grab the mic. This is actually very funny. The question that was asked is, well, aren't prepared statements faster? They can be. But a really funny thing happens when you have when you actually have a type context. Here. That grammar can be remembered because the actual user supplied data has been very visibly separated out. I could actually write a preprocessor to turn that string into a prepared statement. In fact, the database backend can, and simply have a statement cache. Be like, oh, it's another of this form. Let me just extract that for me. Devs love string concatenation. It is flexible for them. It is understandable for them. The very interesting thing is they don't even realize it, but they're writing compilers. They're writing language translators. And that's just part of how they want to go about doing things. When the biggest problem with prepared statements, in my experience, is in the real world, sometimes you just got to tack on a few more clauses. I'm sorry. Every once in a while, there's a weird situation, and you need to be able to say, oh, yeah, throw this extra or clause on. Throw this extra and clause on. You know, go through a loop here. The structure of queries is not always static. Developers know this because when they write their concatenating code, they write stuff that goes ahead and dynamically generates structure. The prepared statement myth is that this never happens, is that it's somehow an exception. It's not actually the rule. The reality is these exceptions happen enough so they become the rule. Yes, devs can always work around it, but how about we make life easier for them? What if the easier way to write something was also the secure way to write it? Why has it always got to be harder? Any other questions? Go ahead.
Yeah, I have a question regarding this session separating problem.
Yeah.
Well, what do you think about the approach taken by Google Chrome, where every tab is basically a separate process? Because that, I mean, unless you're running Windows, processes are fairly good separated, right?
Really? How does that change what's going on the wire? It doesn't. At the end of the day, if process 2 sends, if you have 2 tabs open, and one is at badguy.com and one is at goodguy.com, both tabs have access to the same cookie store. They do. There's always a shared context. Doesn't matter how you architect your code. The very design of the web is enforcing a shared context. When that bad guy tab makes a request to good guy content, I'm going to tell you the good guy cookie is going to be there. It has to be. Because if it wasn't there, the web would not work. The web requires cross-site cookie access, at least by default. It's been required from the beginning. It's been used by DoubleClick since the beginning too, but it's required by every single sign-on system, required by every enterprise system, required by most of the major large websites. If it didn't work, the web would not function. Because of that, it doesn't matter what the process model is. The process model is a neat trick that makes it harder, not impossible, but harder to exploit memory corruption vulnerabilities. This has not been a talk about dealing with memory corruption vulnerabilities. What this has been a talk about is dealing with the fact that attacker-controlled URLs are able to be sent with user cookies. And we don't have a good way to stop that now, 17 years after cookies were created. We need a better way. Any other questions?
I think there are two more problems with this base64 approach.
Excellent.
Yeah.
Someone get this guy a beer.
The first of all is, I think it will fail because you always expect table to be actually base64 encoded when it arrives at the string that is parsed. It doesn't need to be that way.
Whoa, whoa. Let me be very clear because people have screwed this up they've screwed up because I've explained it badly. What is in the database is always clear text. The database has no base64 encoded data inside of it.
I perfectly understand that. What you actually do by encoding it in base64 is that you separate meaning from value.
Yes.
Yes, but you always expect the variable table to be base64 decodable. If it's not, the SQL server is going to fail. You can still escape the SQL code if you somehow manage to pass the encoding.
No. Look. I'm going to actually pull this up here. It's a good question, but here, look.
Yes, you can encode that, but you, on the parsing side, you expect the string to be actually base64 encoded. But I perfectly understand that, but I doubt that you always get, or I am perfectly sure that you get around always encoding the evil string up here, which is red, and into base64 and passing it on to the database. You will always get somewhere where it can pass a string that actually breaks encoding and has this magic terminator character that you expect to be base64. I think the whitelisting won't work.
So here's the deal. There's actually a possible exploit path, and you do deserve a beer. If you have a database in which a function can return not just a bare string, but a string that itself might be recursively parsed as code, then my approach does not help. The reason my approach works is, have you ever written a parser? Like a lexer and a parser? So the idea is the thing goes ahead and it sees, there we go, there's the mouse. It sees a select verb, it sees the count modifier for this star. It's going ahead and picking out each character. Now this base64 decode, quote, base64 encode string. This thing doesn't just return ABC123. This thing returns a parsed token of a certain type. And that type is string, not thing to be recursively reparsed. It returns string. And that's something that is metadata above and beyond what is actually encodable from a particular string. That's why this is interesting. What I had a failed experiment, by the way, where I tried to do implicit tree locking here. So what I tried to do is I tried to have a function called tree lock where I would have tree lock 123, comma, attacker controlled string, comma, 123, and then close. And the idea is then the attacker couldn't know he had to predict 123. Maybe it was 4. It was some random integer. And the problem was that the actual middle value wasn't necessarily being parsed as a string. It could, say, be a subquery. And so the attacker could still go ahead and get arbitrary SQL to execute. What is interesting here is that I'm able to constrain someone to a string going into a function that only returns a string. That's why this is interesting. Go ahead in the back. Do you have the mic? Well, this is getting recorded, so we should move the mic. Also, I can barely hear you.
What I think the gentleman is asking is what if that middle line of code never gets executed? At that third line of code, you're base decoding it, but you're assuming it's base 64. Eliminate that middle line and pass that first string into the second string, and you still have an escape.
Oh, wait. So you're saying what if this was not base 64 encoded in the first place?
Exactly. What if that second line was never executed?
Oh, yeah. Then you're host.
Right.
Yeah. But what Oh, okay. So what I'm saying is that you got to think of failure modes, right? What happens if you forget to escape some data? You know what? The system still works. What happens if you fail to base64 encode the string that came in from the attacker? Well, then, the first time it hits base64 decode, and it wasn't originally base64 encoded, the thing blows up. But the thing blows up in your initial testing phase. That's why base64ing is better than escaping. If you forget to escape, nothing goes wrong. If you forget to base64 encode, the world comes to an end. This is actually not a bug, but a feature. So you're totally right. Like, if you have some situation where that input might not have been encoded, everything is bad. But what I'm saying is, in my system, you detect that error situation really fast because everything has been assuming it was encoded.
Just another note, because yeah, it's a general rant. I don't think it's a good approach, it's base64. I spent most of my day with some of this overpriced, enterprisey database that needs to be administrated. And it takes thousands of SQL queries per second, and users call in and say, oh, the error happened at 4 o'clock. Could you please fix it? And so I have to look at the raw log of the SQL server that takes thousands of inserts and updates per second and parse all that. And you also, already said debuggability. If I understand that correctly, all I get in my raw logs is the base64 encoded input that goes straight to the SQL server that will then interpret this base64 string.
Oh,
your
absolutely.
approach is never going to see the light of day in my realm for any use because I can't debug it.
So unquestionably, if you don't get debugging tools that can actually decode the base64 data, it will never see the light of day. Like, no question. Like, that's part of the work to be done. Yes, you're totally right. And everyone here should hear that and recognize it as the absolute truth. If it is too hard to debug, it doesn't matter if this thing is the most secure thing on the planet. If it is not integrated into the debugging tools that an actual production engineer has to use, screw it, it's never going anywhere. My hope, and I could be wrong, but my hope is that this thing is straightforward enough to include into the debugging, into the actual viewing tools. Only because there's no crypto. If there was crypto, it'd be hopeless. It'd be totally hopeless. Someone else had a question. But I just want to point out, by the way, thousands of queries are not a problem. Base64 encoding itself is so fast, like there's no actual performance hit from the encoding itself. All the performance hit that I'm dealing with, and I'm absolutely dealing with it because it matters, but the actual performance hit is coming from hopping out to a user-defined query. That actual user-defined function link is a little slow sometimes. Thank you. Okay, so you want 3 more questions, or you want me to cut it here? Yeah, that's fine. I like drinks. All right, are there 3? Okay, go ahead.
Guys, just speak up a bit. Okay, you talked about a lot of things, so related to cross-site scripting again.
Okay.
You said it would be great to actually read the history of the user and to see the sites that he had been visiting before.
No, just same domain.
Sorry?
It would be great if I could know. The ultimate thing that I want to know is this navigation that I'm at now. Did this come from me, or is this some other guy who happens to be navigating knowing that I'm logged in? I can't differentiate the two right now. I was hoping that I could look at window.history and say, look at the last thing in history, and if I get something back that is like my own domain, then great. I know theoretically, now I know about the handle issues, but I know that the last guy was still me. But I can't even do that. I don't understand why it should be so hard for me to find out that a particular navigation request came from an authenticated source. It's possible to do right now without having to manually tag each request with a CSRF token.
Right, I was thinking about history stealing, but I think that's too wide and there are too many information there to actually get this information.
Oh, I was just trying to get same domain information. No one cares about history stealing same domain. Doesn't make sense because server logs. It's the same domain. Like the server has logged all the resources that you've received. It would only be interesting if you could history steal cross-domain. Now that being said, clearly at some point in the last 10 years, it was possible to history steal cross-domain because that's what the API looks like. It looks like an array that you used to be able to read, and then they fixed it by saying you can go back, you can go forward, and you can get length, but you can't actually see what the domains are. And if you could see what the domains were if it was same domain, you might be able to implement some useful security, but you can't even do that.
Actually, you can just by looking at link colors. That's a new way. Some people looked at link colors and
yes, but
visited
that
links.
doesn't. So link colors, the colon visited tag in CSS is great, but the problem is that it's not specific enough. So if any window goes ahead and browses to a particular URI, that URI will be visited. I'm trying to think. Ultimately, it doesn't matter because the visited stuff is all getting bug fixed, but there might actually be a way to do the hack that you're describing for, another month. Any other questions? I think I have like one or two more. Go ahead. Bring the mic up to the front. Okay, I'll grab it. You guys are asking really great questions, so I'm having a blast.
So I'm going to ask a stupid question now. I think I was missing something on the interpreter suicide thing that you're saying before. So you basically detect something is going wrong, and you tack this interpreter suicide script in front of whatever you're sending out.
Mm-hmm.
Why, if you're detecting something is fishy anyway, why not just not send out anything?
So the idea is that the server has already sent dangerous content to the client. Like at byte 20,000, there's a bomb. We're at byte 100, and we see that something bad is going to come later. And so we want to prevent ourselves ever getting to the point that byte 20,000 is parsed. My ultimate desired design is that I can check a window new session variable, and if it's set, then I run what I call atomic navigate. And atomic navigate is what I'm actually implementing with interpreter suicide. It's I'm here, and I am here until my parent window navigates me somewhere else. Think of it like I have a script block. Something bad has been detected, and now what we're going to do is do everything in our power to prevent ourselves from ever getting out of that script block.
Okay, so the detection is on the client side.
Yeah, the detection.
And I think that was the misunderstanding with that before, because people were thinking the encoding, the base64 encoding, takes place on the client side, and then people could send you something that wasn't base64 encoded. I think that was the...
The encoding does not happen on the client side. The idea is as soon as the fields come in over PHP, they're base64 encoded, or PHP or Perl or whatever you're using. But as it's parsed out of the HTTP request, the variables are immediately base64 encoded. They are continue to be tunneled in that as the block traverses the application, and it stays base64 until the point where it shows up in the actual database. That's one approach. The other approach is that we actually trust the scripting environment to keep the string, to keep that particular variable in and of itself or unified. And we get all the way to the SQL statement, and now we just need to make sure that the SQL statement, when it's constructed, still keeps the isolation. So that's the late binding model. The early binding model is the thing is base64 encoded the moment it comes off of PHP. The late binding model is it's base64 encoded right as it's put into the SQL statement. Both work. What doesn't work, of course, is if you're doing client-side base64, because then the attacker just doesn't encode it. And you're host. Yeah, you're totally right. All right, I think I'm done for questions. Let's go drink and party.